Well, hello and welcome to the third Thursday webinar. I am Tom Sandry, and this month we're going to be talking about sweep frequency response analysis of transformers. Now, sweep frequency response is a major advantage in transformer condition analysis, allowing visualization of the inside of a transformer's tank without costly detanking. This is done by performing a simple measurement, looking at how well a transformer's windings transmit a low voltage signal that varies in frequency. Just how well a transformer does this is related to its impedance, the capacitive and inductive elements that are intimately related to the physical construction of the transformer. Changes in frequency response as measured by SFRA techniques may indicate physical change that has occurred inside the transformer and thus a change to the transformer's impedance. The cause of the impedance change then needs to be identified and investigated. But let's not get ahead of ourselves. First, we need to understand why the transmission of a low voltage signal along a transformer's winding is influenced by frequency and impedance. No circuit is without resistance, whether desired or not. Resistive and reactive components in an AC circuit oppose current flow. The total opposition to current flow in a circuit depends on its resistance, its reactance, and the phase relationship between them. Impedance is defined as the total opposition to current flow in a circuit. Now, the equation shown is the mathematical representation for the magnitude of impedance in an AC circuit, where impedance, represented by the capital letter Z, equals the square root of the sum of the squares of resistance plus net reactance. All right, let's talk about inductive reactance. In an inductive AC circuit, the current is continually changing and is continuously inducing an EMF. Because this EMF opposes the continuous change in the flowing current, its effect is measured in ohms. This opposition of the inductance to the flow of an alternating current is called inductive reactance, represented by X sub L. Current equals voltage divided by X sub L is the mathematical representation of the current flowing in a circuit that contains only inductive reactance. Now, in the formula, I is the effective current measured in amps. X sub L is the inductive reactance measured in ohms. And V is the effective voltage across the reactance. Now, the value of X sub L in any circuit is dependent on the inductance of the circuit and on the rate at which the current is changing through the circuit. The rate of change depends on the frequency of the applied voltage. X sub L equals 2 pi FL is the mathematical representation for inductive reactance, where pi equals approximately 3.14. F is the frequency measured in hertz, and L is the inductance measured in henries. The magnitude of an induced EMF in a circuit depends on how fast the flux that links the circuit is changing. In the case of self-induced EMF, such as in a coil, a counter EMF is induced in the coil due to a change in current and flux in the coil. This counter EMF opposes any change in current and its value at any time will depend on the rate at which the current and flux are changing at that time. In a purely inductive circuit, the resistance is negligible in comparison to the inductive reactance. The voltage applied to the circuit must always be equal and opposite to the EMF of self-induction. All right, next let's look at capacitive reactance. Capacitive reactance is the opposition by a capacitor or a capacitive circuit to the flow of current. The current flowing in a capacitive circuit is directly proportional to the capacitance and to the rate at which the applied voltage is changing. The rate at which the applied voltage is changing is determined by the frequency of the supply. Therefore, if the frequency of the capacitance of a given circuit is increased, the current flow will increase. It can also be said that if the frequency or capacitance is increased, the opposition to current flow decreases. Therefore, capacitive reactance, which is the opposition to current flow, is inversely proportional to frequency and capacitance. Capacitive reactance, X sub C, is measured in ohms, as is inductive reactance. X sub C equals 1 divided by 2 pi Fc is a mathematical representation for capacitive reactance, where, once again, pi equals approximately 3.14. F equals the frequency measured in hertz. C equals the capacitance measured in farads. The relationship between resistance, reactance, and impedance is shown here. The current through a certain resistance is always in phase with the applied voltage. Resistance is shown on the zero axis. The current through an inductor lags applied voltage by 90 degrees. Inductive reactance is shown along the 90-degree axis. Current through a capacitor leads applied voltage by 90 degrees. Capacitive reactance is shown along the negative 90-degree axis. Net reactance in an AC circuit is the difference between inductive and capacitive reactance. The equation net reactance equals X sub L minus X sub C is the mathematical representation for the calculation of net reactance when X sub L is greater than X sub C. The equation net reactance equals capacitive reactance minus inductive reactance is the mathematical representation for the calculation of net reactance when X sub C is greater than X sub L. Impedance is the vector sum of the resistance and net reactance in a circuit, as shown here. The angle theta is the phase angle and gives the phase relationship between the applied voltage and the current. Impedance in an AC circuit corresponds to the resistance of a DC circuit. The voltage drop across an AC circuit element equals the current times the impedance. The equation voltage equals current times impedance is the mathematical representation of the voltage drop across an AC circuit. Now let's look at impedance in a resistive inductive circuit. Impedance is the resultant of phasor addition of resistance and inductive reactance. The symbol for impedance is capital letter Z. Impedance is the total opposition to the flow of current and is expressed in ohms. The equation impedance equals the square root of the sum of resistance and inductive reactance squared is the mathematical representation of the impedance in a resistive inductive circuit. Now, as an example, if a 100 ohm resistor and a 60 ohm inductive reactance are in series with a 115 volt applied voltage, we can work through the equation and our impedance would equal 116.6 ohms. Now let's look at a resistive capacitive circuit. In a capacitive circuit, as in an inductive circuit, impedance is the resultant of the phasor addition of resistance and capacitive reactance. The equation impedance equals the square root of the sum of resistance squared plus capacitive reactance squared is the mathematical representation for impedance in an RC circuit. Once again, as an example, a 50 ohm capacitive reactance and a 60 ohm resistance are in series across a 110 voltage source, as seen here. We once again calculate the total impedance. And we find the impedance is equal to 78.1 ohms. Impedance in a resistive capacitive inductive series circuit is equal to the phasor sum of resistance, inductive reactance, and capacitive reactance as we see here. Equations: impedance equals the square root of resistance squared plus the product of the product of inductive reactance minus capacitive reactance squared, and impedance equals the square root of the sum of the resistance squared plus the product of capacitive reactance minus inductive reactance squared are the mathematical representations of impedance in a RCL circuit. Because the difference between inductive reactance and capacitive reactance is squared, the order in which the quantities are subtracted does not affect the answer. Now, again, as an example, we'll find the impedance of an RCL circuit where the resistance is 6 ohms, inductive reactance is 20 ohms, and the capacitive reactance is 10 ohms. And our impedance will calculate out to be 11.66 ohms. Impedance in a parallel RCL circuit equals the voltage divided by the total current. Total impedance equals total voltage divided by total current is the mathematical representation of the impedance in a parallel RCL circuit. The primary objective of SFRA is to determine how the impedance of a test specimen behaves over a specific range of applied frequencies. The impedance is a distributed network of active and reactive electrical components. The components are passive in nature and can be modeled as resistors, inductors, and capacitors. The reactive properties of a given test specimen are dependent upon and sensitive to changes in frequency. This behavior becomes apparent when we model the impedance as a function of frequency. The result is a transfer function representation of the RLC network in the frequency domain. A standard definition of frequency response, FRA, is the ratio of a steady sinusoidal output from a test object subject to a steady sinusoidal input, or more simply put, signal output divided by signal input equals response. Sweeping through the frequency range of interest gives rise to the S in SFRA to distinguish it from impulse methods where the response is estimated rather than measured. The basic measurement is shown here. To remove the effect of test leads, a 3-lead system is used to measure both the input and output voltage simultaneously. Coax test leads of 50 ohms are used to apply the source voltage and measure the voltage as V sub in. Consequently, V sub out is referenced against the 50 ohm test lead to ground. Frequency response analysis plots the ratio of the transmitted voltage waveform to the applied voltage waveform in decibels. The response in decibels is calculated via the equation. The response in decibels equals 20 log 10 times the output voltage divided by the input voltage. The impedance attenuates the input voltage signal. Individual passive components such as inductors, capacitors, and resistors have identifiable and distinct frequency responses. In practice, however, there is no such thing as an ideal inductor, an ideal capacitor, or an ideal resistor. Each has elements of the other component. Consequently, their responses contain elements of each component, although denominated by their normal type. The expected response for a short circuit at any frequency is that output voltage is equal to input voltage, as impedance equals 0. This equals 0 dB across the swept frequency range. An ideal resistor reduces the output voltage across the entire swept frequency range. A 50 ohm resistor would give an output voltage half the input voltage. This would be a straight line at approximately 6 dB down, or minus 6 dB, as seen here. A 500 ohm resistor would give a response at approximately 20.8 dB down, or minus 20.8 dB. An open circuit would, in theory, provide infinite impedance and an output voltage of 0. This is not calculable as a decibel value, but equates to infinite dB down. Now let's look at the response of an ideal inductor. An ideal inductor at low frequency looks like a short circuit. As frequency increases, so does the impedance, heading towards an open circuit. The response for an ideal inductor is shown here. It starts at 0 dBs and then shows a characteristic roll-off on the log scale as frequency increases. Now let's look at the response of an ideal capacitor. An ideal capacitor looks like an open circuit at low frequencies, but at high frequencies it looks more like a short circuit. The typical response shows a response which climbs towards 0 as frequency rises, as seen here. Resonance occurs in an AC circuit when the inductive reactance and capacitive reactance are equal to one another, or X sub L equals X sub C. When this occurs, the total reactance equals X sub L minus X sub C becomes 0, and the impedance is totally resistive. Because inductive reactance and capacitive reactance are both dependent on frequency, it is possible to bring a circuit to resonance by adjusting the frequency of the applied voltage. Resonance frequency is the frequency at which resonance occurs, or where X sub L is equal to X sub C. Now, the equation resonant frequency equals 1 divided by 2 pi, the square root of LC, is the mathematical representation for resonant frequency. Let's look at resonance in a series arrangement. At low frequencies, the capacitor will dominate, and the arrangement will look like an open circuit. The impedance approaches infinity. As frequency rises, the impedance and the capacitor will fall, but the impedance of the inductor will rise. At high frequencies, the inductor will dominate, and the arrangement will look like an open circuit. The impedance approaches infinity. The overall impedance of the arrangement is Z, which we can plot against frequency as seen here. The point of minimum impedance is the resonant point, and is where the impedance is equal to the resistance. This occurs when the X sub L is equal to the X sub C. Now, generally for a series combination at resonant frequency, we have the following. The reactance of the capacitor and inductor are equal. Impedance is minimum for given values of capacitance, inductance, and resistance. The impedance of the circuit is equal to the resistance of the circuit. The voltage applied by the source is in phase with the current. The current is maximum for given values of capacitance, inductance, and resistance. The power dissipated in the circuit is maximum for given values of capacitance, inductance, and resistance. Now, if we were to measure this circuit using an SFRA test set, we would plot the resonance in dB rather than in ohms. Using equation, the response in dB equals 20 log 10 times the output voltage divided by the input voltage, and equation voltage out divided by voltage in equals 50 divided by the impedance plus 50. The response D in decibels for an impedance is given by the equation D equals 20 log 10 times 50 ohms divided by the impedance plus 50 ohms. Plotting D for the series impedance of the figure shown yields the graph seen here. Clearly, in decibels, a series resonance yields a maximum. This relates to the capacitive climb followed by the inductive roll-off. The maximum in an SFRA plot, therefore, corresponds to a series arrangement of some form that has reached a resonance. Now let's look at resonance in a parallel arrangement. At low frequencies, the inductor will dominate, and the inductor will look like a short circuit. The impedance approaches 0. As frequencies rise, the impedance of the capacitor will fall, but the impedance of the inductor will rise. At high frequencies, the capacitor will dominate, and the capacitor will look like a short circuit again. The impedance approaches 0. The overall impedance of the arrangement is Z, which can be plotted against frequency as seen here. The point of maximum impedance is the resonant point. This occurs when the X sub L is equal to the X sub C. Now, again, generally for a parallel combination at resonant frequency, we have the following. The reactance of the capacitor and inductor are equal. Impedance is maximum for given values of capacitance, inductance, and resistance. The impedance of the circuit is equal to the resistance of the circuit. The voltage applied by the source is in phase with the current. The current is maximum for given values of capacitance, inductance, and resistance. The power dissipated in the circuit is minimum for given values of capacitance, inductance, and resistance. Now again, if we were to measure this circuit using an SFRA test set, we would plot the response in decibels rather than in ohms. We can plot the response D in decibels for an impedance as given by the equation D equals 20 log 10 times 50 ohms divided by the impedance plus 50 ohms. Again, noting that Z is a function of frequency and is complex. Plotting D for the parallel impedance yields the graph shown. At low and high frequencies, the impedance approaches the value of the resistance, which in this case is 335 ohms. We could calculate the decibels the resistance alone would yield at approximately minus 17.5 dB, as shown in the graph. Clearly, in decibels, a parallel resonance yields a minimum. This relates to the inductive roll-off followed by the capacitive climb. When a minimum occurs in an SFRA plot, this corresponds to some parallel arrangement of an inductor and a capacitor within the transformer. In practice, there is no such thing as an ideal capacitor, an ideal inductor, or an ideal resistor. They each have elements of the other component. To demonstrate, we can look at the response of a small wound coil, a non-ideal inductor. We would see two distinct effects. A low-frequency effect where there is a resistance which prevents the coil having a 0 dB response at low frequencies. A high-frequency effect where turn-to-turn capacitance counteracts the continued roll-off of the inductance. At high frequencies around 200 kHz, the inductive roll-off is replaced by a capacitive climb. This is where the capacitance between the coils of the specimen counteracts the effects of the inductive element. There is another effect in the coil around 1 MHz. This may relate to its construction in layers where mutual inductance and capacitance between layers begin to have an effect. The SFRA response for the coil is shown on a log scale. This representation of data tends to highlight low-frequency responses. The same data using a linear scale is shown here. The resonance around 900 kHz are now less dramatic. The linear scale tends to highlight high-frequency responses. The display of data in log and linear formats helps to identify differences between captured traces. An SFRA open circuit test will show the response of the core and windings, while an SFRA short circuit test only shows the response of windings. Each frequency range corresponds to different components in the transformer. Some general frequency ranges are 20 hertz out to 20 hertz out to 2 kilohertz. Here we typically see main core deformation, open circuits, shorted turns, residual magnetism. At 10 kilohertz out to about 20 kilohertz, we typically are looking at bulk winding component and shunt impedance. At 20 kilohertz to 400 kilohertz, we see deformation within the main windings. At 400 kilohertz out to about 1 megahertz, we typically are looking at tap winding. However, keep in mind that each transformer will have specific responses and the frequency range given is for general reference only. Now, this example shows a typical high voltage Y winding response. All three phases show similar responses at low frequencies with the following characteristics. The center phase has a slightly increased impedance, more negative dBs, at low frequencies. The center phase has one resonance and the outer phases two resonances below about 1 kilohertz. The outer phases are very similar at low frequencies. The three phases come back together as frequency rises toward 10 kilohertz. The three phases show regions of similarity and regions of dissimilarity across the frequency range. Let's look at a high voltage delta winding. This example shows the responses for three phases of a high voltage delta winding. This is a characteristic response at low frequencies. The center phase has a slightly higher impedance, more negative response at low frequencies. The center phase is different to the outer phases at the first resonance below 10 kilohertz. The center phase is more like the outer phases as we rise in frequency. All three phases have the same basic shape above 100 kilohertz. Variations with tap position. This example shows the responses for one phase of a transformer tested at 9 tap positions. Notice that the linear scale is selected since the SFRA changes occur in the high frequencies. The main winding responses below 25 kilohertz remain unchanged. Tap winding responses show stepwise variations. And now let's look at shorted turns. This example shows the SFRA response taken after an incident. One phase has clear inductive roll-off associated with short circuit measurements. Variation is a clear indicator of shorted turns on the A phase. Now let's look at factory results for a high voltage delta. So this example shows the SFRA response taken of the high voltage delta windings at the factory. This example shows the initial SFRA response taken of the high voltage delta windings in the field. The same phase is compared to the factory response upon arrival at the field site. Low frequency responses show offset due to core magnetization. Results are acceptable, but the test is repeated for confirmation. Now, this example shows the SFRA responses taken after demagnetization of the high voltage delta winding in the field. After demagnetization, the low frequency offset is now removed. The high frequency response remains unchanged. Now, some site noise as low dB response is not unusual. Now let's look at the effects of removing oil. This example shows the SFRA response of one phase of a transformer measured with and without oil. The blue trace represents the response without oil. The white trace represents the response with oil. Some site noise as low dB response is not unusual. Removing oil lowers capacitances and resonance shift to higher frequencies. Now let's look at some practical application. In a standard application, a fingerprint reference curve for each winding is captured when the transformer is new or when it is in a known good condition. These curves can later be used as reference during maintenance tests or when there is reason to suspect a problem. Reference results are performed but not essential. Results from a sister unit from the same manufacturer may serve in their stead. Several examples of internal winding movement and related failures being detected by SFRA are available where diagnosis was made without use of reference results. The most reliable application of test is the time-based comparison, where curves are compared over time on measurements from the same transformer. Another method utilizes type-based comparisons between sister transformers with the same design. And lastly, a construction-based comparison can, under certain conditions, be used when comparing measurements between windings in the same transformer. These comparative tests can be performed before and after transportation of the transformer. After severe through faults. Before and after overhaul. And as a diagnostic test if you suspect potential problems. One SFRA test can detect winding problems that require multiple tests with different kinds of test equipment, or problems that cannot be detected with other techniques at all. The SFRA test represents a quick and cost-effective way to assess if damages have occurred or if the transformer can safely be re-energized again. If there is a problem, the test result provides valuable information that can be used when determining further action. To make an SFRA measurement, a transformer must be prepared as it would for power factor and capacitive measurements. Each winding section, high voltage and low voltage, is analyzed separately. Transfer function measurements from high voltage to low voltage may also be made, but these are less effective at detecting movement. Short circuit SFRA measurements, made for example by performing an SFRA on a high voltage winding with the low voltage winding shorted, provides further information about winding integrity and relates to transformer leakage reactance. The open circuit. An open circuit measurement is made from one end of a winding to another with all terminals floating. For a delta winding, connections would be H1 to H3, for example. For a Y winding, measurements are taken from high voltage terminals to neutral, such as H1 to H0. The short circuit. A short circuit measurement is made with the same SFRA test leads connections as an open circuit measurement, but with the difference that another winding is short-circuited. To ensure repeatability, it is recommended that the 3 voltage terminals on the shorted windings are all shorted together. This would mean, for example, shorting X1 to X2, X2 to X3, and X3 to X1. This ensures all 3 phases are similarly shorted to give a constant impedance. Any neutral connections available for the shorted windings should not be included in the shorting process. Interwinding. An interwinding measurement is from one winding to another with all other terminals floating. This would include, for example, H1 to X1 on a double wound transformer, or H1 to Y1 on an autotransformer with a tertiary. Note that H1 to X1 on an autotransformer is not an interwinding measurement, but an open circuit measurement on the same series winding. Interwinding measurements are usually considered as optional tests, or tests for further investigation when open circuit and short circuit tests are inconclusive. Here we see some typical test connections. Here we're seeing test connections for a 2-winding transformer, both for open circuit tests with all other bushings floating, or for short circuit tests where X1, X2, X3 are shorted together and floating. And here we see some typical connections for a 3-winding transformer, both for open circuit tests and for short circuit tests. Now, let's address some frequently asked questions. Is there a published standard for SFRA? The IEEE guide for SFRA is IEEE C57.149, Guide for the Application and Interpretation of Frequency Response Analysis for Oil-Immersed Transformers. Other relevant SFRA documents include the IEC 60076-18, Standard DL T911, and SIGAR Technical Brochure number 342. Are other electrical tests necessary if I perform SFRA? Yes, each test will provide a different piece of data on the transformer. A power factor test looks at the insulation of the transformer. Turns ratio and winding resistance tests reveal the condition of the windings. SFRA provides information about the mechanical integrity of the transformer and can help you determine if a transformer has sustained any mechanical damage. Each electrical test you perform gives you a bit more insight, and together they form a more complete picture of a transformer's health. Sometimes a second opinion from 2 or more tests on the same component can help you confirm a suspected problem. Do I have to perform electrical tests in a particular order? Excitation current and SFRA should be completed first and the winding resistance test last. This is to avoid any residual magnetism from the winding resistance test from affecting the results of the other tests. However, if your winding resistance test is capable of demagnetizing the transformer efficiently after the test, you will not have to worry about the test sequence. Will SFRA work on dry-type transformers? Yes, SFRA looks at the response of the complex RLC network inside a transformer. You can perform baseline or reference measurements on dry-type transformers and compare results over the years. For dry-type transformers, you need to be aware of the effect that ground capacitance can have on the traces. Additionally, the response on the low side may have slight deviations because of low signal levels. A very good ground plane will produce more repeatable measurements. Can I perform SFRA before oil filling a new transformer? Per IEEE C57.149, testing with oil is the most common and preferred method for frequency response analysis. Special consideration should be given to safety when testing a transformer without oil so that excessive voltages are not applied. Presence of oil changes the frequency response. Results obtained with and without oil will cause variations in the SFRA traces. Often, the manufacturer fills and drains the transformer before shipment. You should be aware of the condition in which an SFRA test was performed before shipment from the factory. Does ambient temperature affect SFRA readings? IEEE C57.149 states that large temperature differences, typically much more than 10 degrees Celsius between two measurements, will slightly influence the response at higher frequencies. For all practical purposes, the effect of temperature on SFRA measurements is very small and can be ignored unless there is big temperature variations between the two comparison traces. What is the smallest rated transformer that I can use SFRA on? There is no industry guideline for using SFRA based on a transformer's VA rating. In theory, you can perform SFRA on a transformer of any size, and if subsequent tests are performed under similar conditions, the results can be compared and analyzed. Other electrical tests like transformer turns ratio, excitation current, and DC insulation tests will also give valuable information on smaller transformers. And that concludes our webinar today on sweep frequency response analysis of transformers. Again, we're going to keep the lines open, keeping the webinar open for our questions and answers period. But I would definitely like to thank you once again for taking time out of your busy days to visit us and come see our Third Thursday webinars. I hope these are beneficial to you. We enjoy having you in our audience. So, without further ado, let's get to those questions and answers.